In this lesson, we learn how to use proof by induction to prove divisibility. The steps for proof by induction are: 1. Show it is true for a base case such as when n equals 1. 2. Assume it is true for n equals k. 3. Use step 2 to show that it is true for n equals k plus 1. And 4. Conclude the proof. For example, prove that n squared plus n is divisible by 2 for all positive integers of n. We start with verifying n equals 1. Substituting n equals 1, we get 1 squared plus 1 equals 2. This is true that this result is divisible by 2. Now we assume it is true when n equals k. We substitute n equals k into n squared plus n to obtain k squared plus k. This is equal to 2a because we are assuming that it is divisible by 2. Therefore, the k squared plus k must be equal to 2 times some other number. In step 3, we show that it is true for n equals k plus 1. Substituting n equals k plus 1, we obtain k plus 1 squared plus k plus 1. We expand k plus 1 squared to obtain k squared plus 2k plus 1. We can collect like terms to get k squared plus 3k plus 2. Now we need to use our result from step 2 to help us see that it is divisible by 2. We split the 3k into k plus 2k to give us k squared plus k plus 2k plus 2. Now we can substitute k squared plus k for 2a using the step 2 result to get 2a plus 2k plus 2. Now we can see that this can be written as 2a plus k plus 1. And since there is a factor of 2, this must be divisible by 2. We can conclude the proof by stating that since f of 1 is true and f of k plus 1 is true, whenever f of k is true, f of n is true for all n. Here is another example. We start with verifying that the n equals 1 case is divisible by 3. When n equals 1, we obtain 1 cubed minus 1, which equals 0. 0 divided by 3 equals 0, and so 0 is divisible by 3. Now we assume true when n equals k. Substituting n equals k, we obtain k cubed minus k, and this is equal to 3a, as we are assuming that k cubed minus k is divisible by 3. That is, it is 3 times some other number. We can rearrange this as k cubed equals 3a plus k. Now we show it is true when n equals k plus 1. Substituting k plus 1, we obtain k plus 1 cubed minus k plus 1. K plus 1 cubed can be expanded to obtain k cubed plus 3k squared plus 3k plus 1. Collecting the like terms, we have k cubed plus 3k squared plus 2k. To show this is divisible by 3, we must substitute k cubed for the result from step 2. K cubed equals 3a plus k. We collect like terms to get 3a plus 3k squared plus 3k. Here, a factor of 3 can be taken out, and so when n equals k plus 1, we also get a result divisible by 3. We conclude the proof in the same manner as previously. Here is another example. When n equals 1, we obtain 5 to the power of 1 plus 3, which equals 8. This is divisible by 4. We substitute n equals k to obtain 5 to the power of k plus 3. Because we assume it is divisible by 4, this is equal to 4a. We can rearrange this as 5 to the power of k equals 4a minus 3. Now we substitute n equals k plus 1 to obtain 5 to the power of k plus 1 plus 3. 5 to the power of k plus 1 equals 5 to the power of k multiplied by 5 again. We can write it as 5 times 5 to the power of k plus 3. Now to show this is divisible by 4, we use our step 2 result and substitute 5 to the power of k with 4a minus 3. Now we expand to get 20a minus 15 plus 3, which simplifies to 20a minus 12, which can be written as 4 brackets 5a minus 3, which is divisible by 4. We can now conclude the proof. Here is another example. For n equals 1, 8 to the power of 1 minus 3 to the power of 1 equals 5, which is divisible by 5. When n equals k, we obtain 8 to the power of k minus 3 to the power of k, which equals 5a, as it is divisible by 5. We can rearrange this as 8 to the power of k equals 5a plus 3 to the power of k. When n equals k plus 1, we obtain 8 to the power of k plus 1 minus 3 to the power of k plus 1, which can be written as 8 times 8 to the power of k minus 3 times 3 to the power of k. We can substitute 8 to the power of k equals 5a plus 3 to the power of k like so. Expanding, we get 40a plus 8 times 3 to the power of k minus 3 times 3 to the power of k. This simplifies as 40a plus 5 times 3 to the power of k. A factor of 5 can be taken out like so. Therefore, when n equals k plus 1, it is also divisible by 5. We can conclude the proof. Visit mathsathome.com for further videos and practice.